This lecture focuses on RC circuits, where the R stands for resistor and the C stands for capacitor. And in every problem that we work with this, you have to consider the current flowing through one resistor or equivalent resistor and one capacitor or equivalent capacitor. And we can talk about this for charging and discharging. And you notice the big difference between them is that when the capacitor is discharging, there's no EMF in the circuit. So first I'll take a closer look at charging, and then we'll look at discharging. We've already looked a bit at a circuit like this, and we've said current will flow from the positive terminal of the EMF clockwise in this circuit, and the EMF actually sets up an electric field that will remove electrons from the top plate, so you end up with positive Q on the top plate, and it deposits electrons on the bottom plate, so you get negative Q on the bottom plate. When we're looking with more specifically with RC circuits, though, what we're really looking at is how the charge and the current and the voltage change with time. If we plot the charge as a function of time, we basically have 1 minus an exponential decay function. So the charge starts out at 0, and then it approaches some maximum charge value. And Q is equal to C times V, which means that V is equal to Q over C. So we can actually have an expression for the voltage as a function of time as being this entire thing divided by C. So we end up with just the EMF, or the maximum voltage, times 1 minus e to the negative t over RC. And this e is actually the exponential function, the inverse of the natural logarithm, ln. Where it gets a little more interesting is when we actually look at the current, because the current I is equal to the time derivative of Q, dQ by dt. So if we take the time derivative of this Q function, we get I as a function of time equal to the initial current, I naught, times e to the negative t over RC. And I'm not showing the derivations of these functions. I guess I'm showing the derivation of the current. I'm not planning to show the derivation of the charge as a function of time because it uses a differential equation, and I don't expect many of you to need to be able to do that during your exam. If you would like me to do that, though, just contact me to let me know, and I'll add a bonus video that shows the derivation of Q as a function of time. What's interesting then, though, is that the voltage and the charge both have this sort of 1 minus exponential decay, whereas the current does have an exponential decay. The current starts out at the initial value, I naught, which is the maximum current, and then it eventually approaches 0. And the initial current here, I naught, is equal to the EMF divided by the resistance, R. And this is when time is equal to 0. Looking at the circuit diagram, the only way to get current equal to the EMF over R is when you replace the capacitor with a wire, or in this case it turns out to be true also when time is 0, and that's assuming that the charge on the capacitor is 0. And this reinforces the idea that an uncharged capacitor acts like a wire. So if you're not sure how to find the initial current, remember that an uncharged capacitor acts like a wire, and when we're charging a capacitor, we typically start with the capacitor uncharged. If we look farther on, when time approaches infinity, we see that the current will be 0. And this reinforces the idea that a fully charged capacitor acts like an open switch. And remember that fully charged is a keyword in this case. It's jargon for physics. And it means that the capacitor will not get any more charged than it already is, and you can treat it as acting like an open switch in the circuit. So we've seen that before in terms of the EMFs being the same. Once the voltage across the capacitor is equal to the voltage across the EMF, then current can't flow through the resistor and can't flow through the circuit. This also happens, or it also works, when you actually substitute in t equals infinity, because the current at t is equal to infinity would be equal to the initial current times e to the negative infinity over RC, and anything to the power of negative infinity approaches 0. So it turns out that the mathematical expression for current as a function of time for a charging RC circuit tells us that an uncharged capacitor acts like a wire, and a fully charged capacitor acts like an open switch. And that's coming from the mathematical side, and it also comes from our understanding of how the circuit is set up. Now, I'll talk really briefly about the time constant, which gets the symbol tau, which many courses also use for torque, but this has nothing to do with torque. Anyway, in really basic terms, tau is defined as the value of the resistor times the value of the capacitor. Tau is equal to RC. And really what this lets you do is rewrite the expression. So we would have the charge as a function of time equal to the capacitance times the EMF, and then 1 minus e to the negative t for time divided by the time constant. So it lets us simplify things ever so slightly. Where it's actually quite useful is for comparing RC circuits. For example, you might be given some kind of conceptual question where you have to very quickly identify which circuit would charge the fastest, or maybe you have to rank 3 or 4 circuits. The easier way to approach this is to calculate the time constant for each one, and then a larger time constant means that that circuit will change over a longer period of time. The other way to work with RC circuits is with discharging. And in this case, the circuit is simpler. We just have a resistor and a capacitor. And the form of the charge equation flips. Now it's actually an exponential decay. If we look at the circuit again, we would have positive charge on, I'm just choosing the top plate arbitrarily to be similar. This could be what happens if we took the previous circuit and then just disconnected the EMF and connected a wire across it instead. Anyway, so in this case, if we did that, then the current would actually flow counterclockwise from the positive plate of the capacitor to the negative plate of the capacitor, and it would go through the resistor. So over time, the charge that's built up on the capacitor is going to drop, but also the current depends on the voltage, and as the charge drops, the voltage will also drop, and therefore the current is going to decrease over time as well. So we start out at some maximum charge on the capacitor, and then we get exponential decay over time. What's counterintuitive is that the current function doesn't change form. In fact, the current function, when I write it the sort of simplest way, is exactly the same as before. What does change is that the initial current is different. So we still have exponential decay for the current. Now, the current depends on the voltage across the resistor and the voltage across the capacitor, which are the same thing in this really simple circuit. And the voltage across the capacitor starts out at some high value, but then it decreases as the charge decreases. So essentially, the current starts out at this initial I0 value, and then we also get exponential decay for the current. But the initial current depends on the charge, and it depends on the time constant. And when the capacitor is discharging, it actually kind of counteracts the assumption that we had, or the reasoning that we had, where a fully charged capacitor acts like an open switch and an uncharged capacitor acts like a wire. That really only applies when it's connected to a bigger part of the circuit and the capacitor is being charged by something. When the capacitor itself is driving the circuit, then we have to think of it differently and realize that when the capacitor is driving the circuit, when it runs out of charge, it will have nothing left, no energy left stored in the capacitor to actually cause current to flow. When I was teaching, I used to sometimes ask my class, what can we do to make this more interesting? And I'd get some ideas, and usually somebody would say, hey guys, no, stop, you're giving him bad ideas for the test. And of course the joke is I already kind of knew all of them, but I was trying to turn it around and think of how to make it interesting. Because we all know really that when the teachers make something interesting, what it means for the students is that it's going to be tricky. But it's better to find out what these tricks are ahead of time and to think about how that can happen rather than find out on the exam that, oh no, they thought of a trick that I hadn't yet thought of. And one of the most common ways that they'll make it tricky is to use multiple resistors. For example, here's one with charging where we would have one resistor on the top going down to a capacitor and then another resistor on the bottom. And when you see the EMF, you would know that it's charging. And so really the only thing that we need to really be careful of is to include all of the resistors that have current flowing in them. And so the current is going to be flowing through this circuit that way. Even though the current doesn't literally flow from one plate to the other through that insulator, the capacitor behaves as if current is flowing. So anyway, in this case, the time constant, which is equal to RC, is going to be equal to REQ times C. And in this case, REQ is just R1 plus R2. Another way to make it tricky is to use multiple capacitors. And I'm choosing to put these in parallel because I know that makes the math easier. And so it's a little bit easier to show you right here. So we have R then and C1 and C2 in parallel. And remember that the RC circuit equations were derived with one resistor and one capacitor. So we have to treat it as if we're working with REQ and CEQ. So in this case, the time constant is equal to R times CEQ. And because these capacitors are in parallel, I can just add them up. So we would have R times C1 plus C2. The third way to make it tricky, and it's actually the most common way that I've seen on exams, is to change R and C. So change the resistors and change the capacitors, maybe just resistors, maybe just capacitors, or maybe both, for charging and discharging. So you'd have one circuit that has a whole bunch of things and a switch. And you might have some capacitors charging through some resistors when it's charging, and then you turn the switch, and then the charged capacitor or capacitors then discharge through a different set of resistors. And I'll show an example of this as a separate video because it gets a bit more involved.